For those of you who are very good in math, I would like to derive the period of a simple pendulum using the conservation of mechanical energy. Now, if you're not very good in math, just forget about this. I derived the period of a pendulum in another way. Now I will do it using mechanical energy. It's a little bit more complicated, but it's cute, it's nice. You know, it shows you that physics works no matter how you approach it. Here is the pendulum. And the pendulum, say, is viewed when the angle is theta. So this is the equilibrium position, the pendulum, and the pendulum will ultimately swing all the way to an angle theta max. There's a length L. And the velocity at this point here, let's call this point B, is v of theta. So we have here point A, equilibrium, point B, and let's call this point D. If there is no friction of any kind, then the sum of potential energy and kinetic energy must be conserved. Here, here, and here must be the same, as a constant. I can always arbitrarily choose the level of gravitational potential energy, and I call it U equals 0 at A. So at point B, I would have to evaluate this distance h. This equals L cosine theta. So h equals L minus L cosine theta equals L times 1 minus cosine theta. So at that point B, mgh, remember Massachusetts General Hospital, that's the difference between potential energy between here and here, equals mg times L times 1 minus cosine theta. That is U at point B, and the kinetic energy at that point B where the angle is theta equals 1/2 m v theta squared. So this all holds for point B. Now in point A, U equals 0, and all the energy is in kinetic energy. In point D, the kinetic energy is 0, and all the energy is in gravitational potential energy. So now, I want to write down at point B, U plus kinetic energy is a constant. M G L times 1 minus cosine theta plus 1/2 m v theta squared equals a constant. I call that equation number 1. What is v theta? V theta is the same as d theta dt, which is the angular velocity, times L. This is the angular velocity, for which very unfortunately sometimes people write omega, not to be confused with angular frequency, which is sometimes also called omega. And I like to write down this as theta dot times L. This d theta dt will change all the time. D theta dt is 0 here and has a maximum value here. So now I want to take the derivative of equation number 1, recognizing that phi theta is theta dot times L. Let's first write down this equation with the substitution. Mg L 1 minus cosine theta plus 1/2 m times L squared times d theta dt squared equals a constant. And now I want to take the derivative. This part you may find difficult. So this is the u part, and this is the kinetic energy part. This is a constant, so this is going to be 0 if I take the time derivative. Now, MGL, the one has no effect. The cosine becomes a minus sign, but I have a minus here, so I get minus minus is plus sine theta. And then, of course, I have theta dot. I have to use the chain rule. Plus 1/2 m L squared, and I have to take the derivatives of theta dot square, so that gives me a 2 times theta dot times theta double dot. Chain rule equals 0. This is du dt, and this is the kinetic energy dt. M cancels. 1L goes. The 2 goes against the 2. And here I have a theta dot, and here I have a theta dot. So the whole situation becomes extremely simple. And what do I end up with? I end up with G sine theta plus L theta dot, double dot, equals 0. Now for small angle approximation, sine theta is about the same as theta if theta is in radians. And so what do I find now? That theta double dot plus G over L times theta equals 0. And I say, youpee! I hope I spelled that youpee correctly. Youpee, this must be a simple harmonic oscillator, because I recognize immediately theta double dot plus a constant times theta is 0. And in fact, I can immediately write down that the angular frequency is the square root of G over L, and the period of oscillation, which is 2 pi divided by the angular frequency, equals 2 pi times the square root of L over G. And this is, of course, no surprise. This is a very familiar result. So you see that you can also derive the period of a simple harmonic oscillation in the case of the pendulum, and you can often do that using the conservation of mechanical energy. Whichever method you prefer, it's up to you. It's clear that if the object is a simple harmonic oscillation in X, which it was, remember there was we called the equilibrium position X, this is plus X, and this is minus X. If it is a simple harmonic oscillation in X, then it must also be a simple harmonic oscillation in theta, because the sine of theta was X over L, and for small angle approximation, the sine of theta is theta. So anything that is a simple harmonic oscillation in X will also be a simple harmonic oscillation in theta.